Good morning everyone. Myself Pranav Limaye. This is the fifth day of Astronomy Week celebration planned by the students of Astro Club of Fergusson College. Till now, the event has been very good, starting right from Big Bang up to an eye-opening session on optical astronomy. But what if we can go beyond our eyes? What if we can see beyond our vision? That's where this remarkable and fairly young field of astronomy comes into picture, right? I am talking about radio astronomy. So, I welcome you all to embark upon this journey through the radio web. I would like to keep you awaited, so let's get started right away. So, the most important and fundamental thing to understand over here is that radio waves are electromagnetic waves, just like light. Now, in your high school days or school days, you must have heard about what are electromagnetic waves. They are just electric fields and magnetic fields mutually perpendicular to each other and perpendicular to the direction of their propagation. Radio waves are also electromagnetic waves and have been allotted a low frequency, that is a higher wavelength position in the complete electromagnetic spectrum. Well, this is the complete electromagnetic spectrum known to us, starting from radio waves at the lower frequencies reaching up to gamma rays at the higher frequencies. Space-based telescopes like Hubble, Spitzer, Chandra X-ray give us the readings of the higher electromagnetic spectrum range consisting of gamma rays, X-rays, ultraviolet, also visible, while the ground-based radio telescopes as ALMA, GMRT, VLA, etc. gives us the observations of radio astronomical data. All these electromagnetic wavelengths with all these observations work in cohesion to give the best results and outputs in order to know how this universe works. Here is an animated image of how and from where such kind of astronomical observations are done. As you can see from the image, there are some black or brown patches and some small openings. The area covered by the brown patches denotes the wavelengths which are blocked by Earth's atmosphere or the interstellar medium. For instance, the electromagnetic waves like gamma rays, X-rays, UV light is reflected back by the atmosphere of the Earth. However, the infrared spectrum is simply absorbed by the atmospheric gases. So the only gaps open for us to make ground-based observations is the visible light spectrum and the radio spectrum. For all the rest wavelengths like gamma rays, X-rays, we can't just do their observations and analyze the data sitting at home. For them, we need some space-based probes which are orbiting outside the Earth's atmosphere to take their observations. Also, the window open for visible light is too small. The light coming from stars, distant galaxies can easily be scattered by Earth's atmosphere and they will never reach the visible light observing telescopes. So, in visible spectrum, we need telescopes like Hubble, which takes beautiful images of distant galaxies and provides excellent analysis of them. However, a fairly large gap is open for the radio spectrum as seen from the image. So, radio waves easily reach Earth, and the science behind it is radio waves are the lowest frequency waves, meaning their wavelengths are very high. So, any obstructions, any dust particles coming in their way, they can simply overpass them. So, radio astronomy is really a new yielding field in the field of astronomy. What's the sole purpose of doing radio astronomy? I must have cleared this point in the previous slide, but still I would like to give a brief info and a more clearer idea in this context. Firstly, radio waves are not blocked by clouds and are not affected by Earth's atmosphere, so they readily reach us. Secondly, unlike visible light telescopes or the optical telescopes, radio telescopes can be used in daytime as well as at night. Radio waves are unaffected by interstellar medium as they pass through free space. Interstellar medium means the dust particles or debris present in the free space all over the universe. For example, meteors, asteroids, the remains of comets, etc. all account for interstellar medium. However, there is one exception. Radio waves are affected by the interstellar plasma, but I won't like to get into it right now. Moving ahead, radio telescopes can detect cool clouds of hydrogen gas in space. Hydrogen is one of the basic fundamental elements responsible for the birth of this universe. Starting right from planets, stars to galaxies, everything was formed due to fusion of hydrogen gas into higher order elements. This gas still prevails in the empty universe and shows its existence through emission of a particular radio frequency. If we are able to catch this frequency, we can reach to the roots of the beginning of stars, the beginning of galaxies, in fact, the beginning of everything. This image shows a scene from the science fiction movie Contact. Here, and the leading actress is sitting beside one of the radio telescopes of the very large array. She has her earphones on and is listening to the radio data coming from the telescope. This is one of the biggest blunder that any science fiction movie can afford as long as a scientific viewer is concerned. The most important point to note in radio astronomy is that we cannot listen to radio data. Radio waves are electromagnetic waves and not sound waves. However, keeping this blunder aside, I would still like to recommend this movie to you if you are a true fan of science fiction. Getting the first cosmic signals. There's a really interesting story behind the birth of radio astronomy. The first detection of radio waves was made by James Clerk Maxwell in the late 19th century. Shortly after that, the first short-distance radio communication methodology was developed by Sir J.C. Bose and Hendrik Hertz. In the 20th century, in the starting of the 20th century, Guglielmo Marconi became the first man to develop a large distance-based radio communication system and thus gained the name of the father of radio communication. Up till now, we had advanced a lot in radio waves. However, it was not up till the next 30 years when, in 1932, the first cosmic signals were fetched by an engineer named Carl Jansky, who was a fellow engineer working at the Bell Labs. There's one more interesting story behind this event. As I said, Carl Jansky worked as a fellow engineer at Bell Labs. Bell Labs used to develop machinery and equipments for long-distance communication systems. Once, the lab was working on its prototype for the transatlantic communication, which was to be made between United States of America and some part of Europe. However, there were some noise interferences in the communication. After eliminating every possible noise interference from human origin, still there persists some noise interference in the communication. So, Carl Jansky was given the job for finding out and rooting out this noise interference. So Carl Jansky, along with his antenna, started to look for the noise interference. As you can see from this image, the antenna sits on a very long base, which is 360-degree rotatable, so that you can view the radio sources from each and every direction. Carl Jansky made his observations for a few months and eliminated the possible causes of noise interferences due to lightning and other human origin noise interferences. However, some part of the noise interference was still there. Carl Jansky was fed up. He took more observations for more months and observed that the noise source from where the interference was coming was actually shifting along the sky. After lots of days and weeks of critical data observation and analysis, he came to a conclusion that the noise interference produced was not of human origin or was not of this world. He then concluded that this noise was actually the cosmic signals coming from the heart of our own Milky Way galaxy. The heart of our own Milky Way galaxy consists of a supermassive black hole, millions of times heavier than our Sun. Around the supermassive black hole lies a city of chaotic stars called as the Sagittarius A. Here you can look at the image of the center of the black hole. At the center of the Milky Way galaxy. As you can see from the image, it's not just an optical image. There are some pinkish and bluish regions or halos or lobes. So this image is a combination of optical, radio as well as X-ray data. This is how all these observations work in union. Now let's talk about the basics of radio telescope. The most fundamental building block of a radio telescope is a radio antenna. Antennas are usually made up of metal due to their high conductivity. Now when the radio waves coming from outer space strike the antenna, the molecules of the metal start to vibrate and in turn they send out analog electrical signals. The next part of a radio telescope is a large enough radio dish. Now from its appearance it may seem that a radio dish is the most important part of any radio telescope. However, the only function of the radio dish is to collect all the radio waves which are incoming and focus them on to the antenna so that we can get maximum strength. I will come to this point later in this video. Now third but not the least, the most vital part or a building block of a radio telescope is the receiving part and the data analyzing part. Nowadays, data analysis is done using computers due to their high processing speeds, complex algorithms, programs, etc. However, computer can understand only digital language and the signals coming from our antenna are analog in nature. So we need some kind of a electronic interface between analog signals and the other end of the system so that the analog signals are converted into digital signals. And the last step is that you have to use a well-known software for the analysis part, and yeah, you are done with your own radio telescope. So I am also going to come to this part later in this video. The following schematic depicts the working of a simple radio telescope. Here you can see that we have a large parabolic dish as seen in the image. There are radio waves incoming from a distant radio source. As these radio waves hit the parabolic dish, they get reflected and converge at a focus where we have kept another reflector. This reflector will gather all the radio waves at its focus and will send the radio waves, that is, reflect them back to the center of the dish where we have our antenna kept. The structure around the antenna is often called as feed horn. The only purpose of feed horn is to prevent any loss of radiation due to scattering. Now, earlier I may have said that the point at which the radio waves are converged, there we keep the antenna. However, in this case, we have kept the antenna at the center of our dish. The only practical reason for this is that after the antenna, we have to connect all the electronic circuitry immediately at the output. If we introduce a cable over here, then we have a huge signal loss. So it's easy that we place our antenna at the center of the dish and take down it through the telescope mount through the electronics, and then with a wire cable we pass the signals to a receiver and amplifier. So why do we require an amplifier over here? The radio waves which are incoming may be from 1,000 light years away from us or even millions of light years away from us. So they are very weak signals. So we need to amplify these signals so that our computer or the receiving system can record the data and do analysis with ease. The receiver and amplifier detects the radio signals, and as I said earlier, computer understands only digital language. The incoming radio waves are converted into digital signals and fed to our receiving system. Computer's only purpose over here is to record the data. The main function is done by the complex algorithms, programs or softwares which we use in the computer. This is an image of a practical radio telescope. This is the Green Banks Radio Telescope located in West Virginia. As you can see from the image, we have a big parabolic dish which reflects and gathers all the radio signals at the focus where we have the receiver. But this is one part of the receiver which reflects the received signals at the center of the dish where we have kept our antenna in a cylindrical structure we call as the feed horn. From there, the radio signals are passed on for processing. Just below the radio telescope you can see a small room kind of a structure. Yeah, this is our control room where all the data is gathered and processed. A large number of computers or even supercomputers are used for the processing and analysis of these radio signals done by research scientists as well as engineers. It is this control room from where people or scientists all over the world get the data for the astronomical sources they are looking for in order to make their studies. The term resolution is commonly used for measuring devices. Its layman definition is how small a quantity your measuring device can detect or measure. For example, consider a 15 centimeter meter scale. Now, what's the shortest length your scale can measure? It's 0.1 centimeter. That's the resolution of your scale. The term angular resolution is used in the fields of observational astronomy, such as optical astronomy and radio astronomy. Its meaning is from how small or how big an area in the sky your telescope can get either light or radio signals. The formula for angular resolution is theta equals 1.22 lambda by d, where lambda stands for the wavelength of the signals we want to receive and d stands for the diameter of our telescope. In case of radio astronomy, the diameter of your radio telescope. So as you can see, as we increase the diameter of our telescope, the value of theta will decrease. It's always beneficial to have a lower value of theta if you want to pinpoint at specific radio sources in sky. Now let's have a look at a quick example to get more clear idea about this concept. Here is an image of one part of the universe. The bright spots you can see are the galaxies. Now, if I want to study the galaxy I am pointing at, I would have to direct my radio telescope in that direction in order to gather the radio emissions coming from the particular galaxy in order to know more about it. But single dish radio telescopes like the Green Bank's radio telescope, which I mentioned earlier, can't pinpoint to the exact galaxy. The circle which I show here is the angular resolution, or the area from which the radio telescope will be getting the radio signals. So even if the circle is covering the radio galaxy we want, it is also covering other neighborhood galaxies which will also send their signals and be detected by our telescope, which will in turn generate some false errors, and that we don't want. But now you can say that from the formula of resolution, as we increase the diameter, we get better pinpointing at our source. But for pointing at the source like this galaxy, we at least need a diameter of few kilometers, and constructing that a big radio telescope is not practically possible. That's where the concept of radio interferometry comes into picture. The answer to our problem is radio interferometry. As seen from the diagram over here, we can see there are two radio telescopes separated by a distance b, which is called as the baseline. We have also made some modifications in the formula of our angular resolution. You can see theta is equal to 1.22 lambda by b, where b is the distance between the two telescopes rather than their individual diameters. So we can always keep the two radio telescopes a few kilometers apart. It's practically possible. So if we want to increase angular resolution more and more, we have to keep the two radio telescopes more and more far apart. Over here in this example, the distance between the two radio telescopes is 30 km, and which gives the angular resolution of 1 arc second, which is much way better than using single dish radio telescopes. The only critical thing in radio interferometry is the electronics. As you can see from the diagram, the radio signals coming and hitting the radio telescopes have different timings. The radio signals will hit the telescope on the left hand side at first, and then the telescope at the right hand side secondly. So we need some phase delay circuits in order to get both the radio signals received by both the radio telescopes at the same time and then do its analysis. Here is an image of the Very Large Array located in New Mexico. A radio interferometer with sufficiently high number of radio telescopes is often called as a radio array. The VLA has a total number of 28 radio telescopes arranged in the Y structure, as you can see, to form an array. Now, the equivalent distance between the arms of the radio telescope corresponds to a single dish radio telescope whose diameter will be 36 kilometers across. Now, from the image you can see the array is placed in a Y-like structure. This iconic Y structure is not for looks, it's for function. The wider an array is, bigger is its eye, and hence greater is its resolution. Let's come back to the image of the universe we saw previously. Now, if we want to point out the galaxy which we wanted to point out using a single dish radio telescope, we will be using the Very Large Array. The angular resolution of the Very Large Array is very high compared to single dish radio telescopes. The circle shown over here depicts the angular resolution of the Very Large Array. So, the Very Large Array can almost precisely point to the galaxy we want, so that we can study the galaxy in more detail. Now, let's take a look at the most active radio telescopes all over the world. First is the Arecibo Radio Telescope located in Puerto Rico. It is the second largest radio telescope on Earth. The main aim of this radio telescope is to search for extraterrestrial life. In 1974, a pictorial message was broadcasted by this radio telescope towards the M13 star cluster, although it will take some time for our message to reach there since the cluster is 21,000 light years away from us. But let's hope for the best. Secondly, the second telescope is the Parke telescope. It is the largest radio telescope which is mobile. It is located in New South Wales in Australia. The main motto of this telescope is to make observations of the pulsars. Next comes the Very Large Array, which we have seen earlier. It's located in New Mexico and does the work of gathering and observing plasma ejections from supermassive black holes. It also does the important work of tracking the spacecrafts released by NASA and ESA. Next comes the CHIMES telescope. This is a fairly new telescope which has used a fairly new design. The CHIMES telescope make observations of the hydrogen line emissions from gas clouds in the universe. We will come to this point later in this video. Last but not the least is our own GMRT. It's located in India in a town called Narayangao nearby Pune. The main focus of GMRT is to make observations of pulsars and galaxy formations. Now, let's move on further towards the theoretical concepts in this video. I would like to share with you some important discoveries in the field of radio astronomy. First one is the detection of 21 cm hydrogen line emission. Second is the evidence for existence of dark matter. The third is quite a new concept to us. It is called as fast radio burst. Other than these, there are n number of discoveries made in the field of radio astronomy. However, these three discoveries are a major breakthrough in the field of astronomy. Now, let's take a look at them one by one. The 21 cm hydrogen line emission. Hydrogen has prevailed in our universe right from the beginning. It was one of the first elements formed after the Big Bang. Hydrogen gas hovers across our galaxies, around stars, in great abundance. A question will arise to you now that how we detect a gas cloud using radio telescopes. Fortunately, we know that hydrogen gas in interstellar space emits radio waves at a specific frequency of 1420 MHz, which gives a wavelength of 21 cm, thus getting its name as the 21 cm hydrogen line emission. Here is a graph which denotes a raw data of hydrogen gas observations The telescopes are tuned at 1420 MHz so that you can see a peak at 1420 MHz depicting the presence of hydrogen gas around a specific star or in a specific galaxy we want to study. After knowing the characteristics of this graph and doing extensive analysis, we get to know more details about the stars and galaxies we want to study. Now let's take a look at galactic rotation curves. Firstly, we must know what a galactic rotation curve is. Every galaxy we know has a supermassive black hole residing at its center, which we usually call as the galactic nuclei. All the other stars and space debris in that galaxy revolve around this galactic nuclei. These galactic rotation curves of the stars revolving around the galactic nuclei gives us concrete evidences of the presence of dark matter. Now we shall take a look at this graph shown over here. It is a graph or a plot of the distance of a star from the center shown at the x-axis and its velocity given on the y-axis. From classical theory of physics, we know that if we consider an object revolving at around a particular point, it will start losing its speed as it goes farther and farther away due to loss of angular conservation or angular momentum. We apply the same theory in studying the galactic rotation curves of stars, and the dotted line you see is the assumptions. That is, as we observe stars that are farther away from the galactic nuclei will lose their velocity eventually. However, that is not the observed case. The observed case is shown by the colored line, which is right above the dotted line. Now, as we go away from the nucleus or the galactic nuclei, the speed of the rotation of stars remain fairly constant. Now, that's a bit unusual. Eventually, scientists made prediction that there must be some undetectable mass present in the galactic arms which is causing the stars to maintain their velocities. It was then named as dark matter. Now let's come to the most exotic discovery made in radio astronomy. Yes, the fast radio burst, the mysterious signal coming from the universe. Fast radio bursts, or FRBs as they are called, are brief bursts of radio waves lasting only for a few milliseconds. Up to this day, around 50 such kind of radio signals have been recorded by radio telescopes all over the world. The first FRB was detected by Dr. Jamie Lorimer in the year 2007 using the Parke's radio telescope. Therefore, fast radio bursts are also called as Lorimer bursts. Here is a graph depicting the first detection of FRBs using the Parke's radio telescope. You can see time scale on the x-axis while the frequency scale on the y-axis. In one of the first slides, I had told you that radio waves are unaffected by any dust particles and clouds in any medium or space. However, they are affected by interstellar plasma. Radio waves coming from a source at different frequencies get delayed due to this interstellar plasma. Thus, you can see a change in frequency as the time passes in the fast radio bursts over here. Now let's take a look at the new frontiers for observing fast radio bursts. The following image depicts the CHIME telescope, which is located in Canada. CHIME stands for Canadian Hydrogen Intensity Mapping Experiment. This telescope at first was solely meant for making hydrogen line emission observations. However, due to its technological aspects as well as observational aspects, it is now being used for observing these unknown signals. The structure of the CHIME telescope is a bit weird. It is elongated and cylindrical in nature. Parabolic dishes like Parke's radio telescope or Arecibo are used to get better resolution and to pinpoint the radio sources in the sky. However, the CHIME telescope, due to its design and structure, traces a particular band in the sky. So, instead of pointing out at radio sources, the CHIME telescope makes observations in a particular band in the sky so that no such event like a fast radio burst be missed out. Till now, I made you familiar with the working of one of the largest and advanced radio telescopes all over the world, and how do they do the observations of different astronomical sources. Now let's take a look at how you guys can build a radio telescope of your own and be amateur radio astronomers. The list of material required is as follows. This list may seem a bit complex, but the components are easy to fetch either online or from the local market. The components are a large enough parabolic dish, low noise block, noise filter, signal processing device, and at last the data analysis software. Let's start with a simple parabolic dish. A normal Tata Sky TV dish will also suffice for beginners. The next component is the LNB or the low noise block. This block contains our antenna and the electronics used for amplifying the received radio signals. Third block is also important, the noise filter. The radio signals which we are receiving are coming from outer space, so they are very weak. Whereas the radio signals on which we listen our radio, such as 93.5 MHz, 101.0 MHz, are fairly strong, and they can easily interfere with the radio signals we want. Hence, a filter is fitted at the output of the LNB so that it filters out all the interferences coming from the radio channels and gives a pure radio signal that we want at the output. This image of the filter shown over here depicts the filter used for getting 1420 MHz. It's called as the 1420 MHz band pass filter. Hence, it is used for making observations of the hydrogen line emission. Next component is the data acquisition device or the signal processing device. This is called as an SDR dongle. This will convert the analog radio signals coming from the antenna into digital signals and give it to the software which we will be using. The most common software used by amateur radio astronomers is SDR Sharp. You can get this software for free on the site RTL SDR. This is a basic software which depicts the frequency on x-axis and the gain of the antenna on y-axis. Combine all these components and you have the first radio telescope. I would like to introduce you all to the young radio astronomers of Fergusson College. This was the first radio telescope built by the second year students of the college. This is the students making observations of the recent solar eclipse which occurred on December 26, 2019. Our juniors are also not left behind. They also contributed by making their own radio telescope and observed the solar eclipse. So, once you are amused by this intriguing field of astronomy, there is no stopping further. Here are some important references wherein you can get some more information and study material in the field of radio astronomy. The first one is the National Center for Radio Astrophysics, which looks after the handling and working of the GMRT. The next one is the National Radio Astronomy Observatory, which looks after the handling and working of telescopes like ALMA and VLA. The knowledge you will gain from these two sites is sufficient enough to direct your journey into the field of radio astronomy. Thanks everyone for tolerating me for such a long duration. I would also like to thank the Astro Club of Fergusson College for giving me this opportunity.